right.
And I wanted to know the hours you did yesterday, if you could sign for them.
Sure. All right, I have everybody's quiz, right? And everybody's name was written on everybody's quiz, hopefully. So, okay, awesome. How was it? Good? Interesting discussions, hopefully? Thank you. Okay, so on Tuesday, we talked about fractions, decimals, and percentages. And it dawned on me that at no point in time did I ever actually define what a percentage is. I just sort of assumed that you guys knew. And not that I don't think that you know, but it's worth actually having a discussion about. So what is a percentage? A fraction? Written in decimal form. But when I say 25%, there's no decimal. Oh, interesting. Okay. Other thoughts? Yes, ma'am?
Is it like a portion of another number?
A portion of another number? Can you say more about what you mean by that?
Like when you say 25%, it's 25% of something.
Okay. So for all of these types of representations, you must know what you're talking about, right? So you don't just walk in a room and say 2/3. People will look at you like you're crazy, right? Like you walk in a room and say 2/3 of everybody in this class is signed up for 394 next quarter, right? Oh, by the way, they screwed with my schedule. So if you were trying to avoid me by signing up for an afternoon class, or trying to stay with me by signing up for the morning class, it's now all screwy. So I'm now going to be teaching the 394 at 3 p.m. Just FYI. So hopefully if you wanted to stay with me and you already signed up for 8 a.m., it's not too late and you can still work the schedule. Jesus Magana is going to be teaching the 8 a.m. class. Jesus? He's new to doing these classes. So what were we saying? Oh, yeah, so fractions, right? So you say 2/3 of something, right? And likewise, when you say 33% of what, right? So you have to first conceptualize what your whole is, no matter what, right? Regardless of if you're talking about fractions or percentages, or decimals for that matter, right? Like what does the 1 represent in the 1's position for a decimal? Is it 1 candy bar? Is it $1 million? What is it, right? So you need to conceptualize what your whole is. Now the thing that's special about percentages is I also think of them in terms of fractions, where I've sort of forced the denominator to be what number? 100 per cent, right? So when I say 25% is 25 things if I have taken my whole and divided it into 100 parts, right? Cent is the prefix for 100, century, centimeter, right? Okay, so per cent. Or if you're like in Spanish, it's por ciento, right? Same idea, right? So, okay, so that was important. I felt really guilty for not having said that. But that also gives us some information, right? That means that if we're trying to think about what are sort of like, quote, the easy directions for converting between representations, what are the easy directions? If I give you a decimal, it's easy, quote, easy, to convert that into what form? What do you think? I heard somebody say fraction, and I heard some people say percent. I'd say both, right? Super easy to do both. Why is it? Okay, so you guys are already convinced that it's easy to convert to a percentage. But why is it so easy to convert directly to a fraction? So if it's a terminating decimal, at least, let's just go with that, right? If it's a terminating decimal, it's really easy to convert to a fraction, because as long as you can say the word, then you can write down the numbers, right? If you have 0.375, as long as you can add thousands, then you've already written it as a fraction, right? 375 divided by 1,000. So terminating decimal, now we did some fun on Tuesday figuring out what happens when you have non-terminating but repeating decimals. And that was okay, so admittedly that was a little trickier. But there was a fun thing there. Okay, what if I give you a percentage? So if I give you the percentage 57%, over 100, right? I say 57%. I'm already saying it out loud, right? 57 divided by 100, okay? But then you can, I don't know, maybe this was not so convincing. But I feel like, maybe we just convinced everybody that it's not that hard to do any of them. Yeah? Okay, cool. All right, so let's move on. So how do we model adding, subtracting, multiplying, and dividing? Fractions, right? Because we spent a lot of time building up our thinking about those operations in the context of whole numbers, but now we've introduced a different type of number, right? So now we've introduced fractions into the picture. And so as you guys, well, not too many of you dived into that. We had one group, where did my group go that did the fractions? You guys did the fractions. And it was like an experience, yeah? A gift of numbers. Okay, so this is where things start to get tricky for kids, right? And so we want to provide a lot of support there. Okay, so let's just get to it. Okay, so what do you need in order to subtract two fractions? Add or subtract two fractions. Well, you need two fractions. That is correct. Okay, so maybe good start. Here we go. So let's say I want to add like 2/3 plus 3/5. Is it really easy to do that as written? As written, there's like an impediment to my goal, right? There's an obstacle in the way. So if I want to add these, I've got work to do. Versus if I wanted to add these, is there much? No. And what's the difference between these two addition problems? Common denominator, right? So if the fractions have the same denominator, adding and subtracting them is really easy. If they don't, then it's not as easy. But why is that? Why is this easy? Yeah, 2/4 and 1/4, we're talking about equally sized pieces already, right? So if I already have equally sized pieces of something, then I can combine those equally sized pieces and still be talking about them in terms of those sizes of pieces, right? But up here, I have different sized pieces. So combining those is now non-trivial, right? Now I've got to figure out how these size pieces compare to each other before I can really do anything with them. Okay? So that's the why behind the rule of get a common denominator before you add or subtract, right? You need equally sized pieces. So sometimes, though, people don't just memorize a rule about having a common denominator. Sometimes people go so far as to actually writing down a formula like this. So this says if I have the fraction a plus c, then I can multiply the two denominators together, right, to make my common denominator. And so if I do that, I have to multiply like a times d and b times d. Have you seen this? So in order to make a common denominator, I need a d here, right? So I'll multiply bd. But if I multiply the bottom by d, then I have to multiply the top by d. And then I need to multiply by b here. But if I multiply the bottom by b, I have to multiply the top by b. And so now that they have a common denominator of bd, I can add the ad plus bc. Yeah? Okay. Can you apply that formula to this addition problem? Take a minute to use this formula to add 3/8 plus 1/4. And then once you've used the formula, I want you to reflect on whether or not there was an easier way to do it. I'm going to make a constructive criticism comment. I know. Well, I'm actually looking over here, so you wrote a 5, sort of like in the middle of the fraction bar. And conventionally, that would mean you're only multiplying the numerator. Okay. And I know that you meant to do both, right? So you write 5 over 5 times 2/3. And then... Okay, yeah. But so then when you add the fractions, do you add the denominator? No. Talk to your group. How you guys doing with this formula? Oh, you didn't use the formula. You did not follow instructions.
I just didn't break off into two. I mean, you technically don't have to do anything to the 3/8, right? Or,
That's correct.
You could multiply it by 1.
So that's part C, right? Is there a better way? Yes, there is a better way. But I wanted you to experience it. So much resistance.
I know.
Okay. Hey, we lost one. No, you moved. No, we lost one.
You lost one.
Oh. Is she okay?
Okay, we have a question.
Yeah.
So, do you, have to use that formula, or can you do something like this?
So that's what part C is for. So I'm asking you to use the formula.
Okay.
But then I'm also asking you to do it your own way.
Oh. So I can use... No, what if that's how we do it our own way?
Wait, what?
Don't think
What
it's
easy. So if you use the formula, what is your denominator?
32.
32.
Yeah.
Yeah.
Because if you try to do the other way,
4 times 8.
oh, maybe I did my
Right, but it's not actually necessary to use that formula, right? Right.
Oh.
There's an easier way.
There is a much easier way. But I want you to do both, right? Like if I give you a formula, I want you to be able to use it. Mostly because how'd you guys do? and then your easier way was just to create. Okay. Done. Okay, so there was a little bit of resistance in the room to following my instructions. In particular, I saw a lot of people like just not wanting to use my formula. It's almost like I'm being successful as a teacher. Yay! Right? Because why is it? So, okay, now that being said, it is important that you're able to read a formula, understand it, and use it. Okay, that is a mathematical skill that is relevant still. Okay, so if I say apply this formula, then you should be able to do that, regardless of how many other cool ways you have to do a problem. Okay, so what does that look like with 3/8 plus 1/4? To use the formula, you're saying, all right, so 3/8 plus 1/4 is the same as 3 times 4 plus, what is it? 8 times 1 over 8 times 4. So you get 12 plus 8 over 32 is 20 over 32. Yeah? Is that really like the optimal way to do this addition problem? Heck no, right? So what would have made our lives so much easier? Okay, so rather than blowing up our denominator by multiplying these together, we could instead identify what we call the least common denominator, right? Which is 8 in this case. So we could instead say 3/8 plus 1/4, where we multiply top and bottom in the second fraction by 2. Now, let me ask you a quick question. When we do this process, multiplying the 2 on top and bottom, what are we actually multiplying by? 1. Right? When you multiply by 2 divided by 2, that number is 1. And so we know that we haven't changed the problem because any number times 1 is always that original number. Which property is that? Multiplicative identity, right? 1 is the multiplicative identity. Everything's connected, right? Okay. So we've got 3/8 plus 2/8 is 5/8. So now I have the challenge of asking myself questions. Because they don't look the same. If I'm learning fractions for the first time, I look at the first number and I'm like, that number's definitely bigger. Why am I saying that number's definitely bigger? Because there's a 20 and a 32 instead of a 5 and an 8, right? Like the numbers in it are bigger. So how do you convince a child that these are equivalent? So you could rewrite 20 over 32 as 5 times 4 over 8 times 4. Yeah? And now notice again what's happening. We're multiplying by a 1. Which means you just have back the 5/8. Okay? Cool. All right. Now, that was all still fairly abstract, yeah? And the reality is you're probably not going to you're not going to start that abstract. So let's talk about how you could use models to do these operations, okay? So I want you to think about this in groups. Are you ready? Are you warmed up enough to try this without me doing anything first? So 1/2 plus 1/3 using an area model. And a number line model. I have not taught you this.
The area model?
Oh, yeah, that's you just show like a square rectangle or something. Yeah, yeah.
Okay.
So I got you started. It wasn't that much help, though, right? I drew 1/2 plus 1/3.
Yeah. So like that's what I have, and then it's like, okay.
So now the real issue is how do you combine those? Because this shaded piece is different than that shaded piece.
I think we can turn that into 6 pieces,
Yeah.
Ah.
So
and then we have 3 pieces. 3 over 6 are equal to 1.
It is a lovely idea. What do you guys think? Oh, I don't see a diagram. That's just abstract still. So we need a diagram.
So first we have to find the common denominator, and then we can draw a diagram, right?
Well, you should. So I want you to think of it more in terms of how could a diagram motivate that process, right? So if I don't know already that I have to have a common denominator, when I look at that picture of 1/2 and 1/3, and I say I want to add those two things, what is my immediate problem?
They're not equal the same thing.
They're not the same size, right? So I can't add those pieces until they're the same size. So what could I do with that diagram so I have pieces that are the same size?
Add so they can put it together and then divide it evenly.
Well, I can't put them together until I have the same size pieces, right? So you want to divide up those diagrams so that they are made of equal size pieces. So how many times do you need to divide the one on the left by? Yeah, and then the one on the right.
The one on the right's already fine, I thought.
No, you have to make it equal the same. So for the first one, would it? You have.
The first one is 3.
So if you divide the 1/2 into 3 pieces, one that's on the right? No. So okay. So then that means I need to do whatever I cut that into the same as the size that I cut the first one into. Right? Beautiful.
So that's kind of how
I like the picture. So you figured out. Cool. That's good. Oh, now our ones are different sizes. Oh, wait. Oh, wait. So remember, anytime you draw one of these rectangles, like if you draw this rectangle to represent, what are you representing here? 1/3? Okay, so I'm looking at the not shaded part in this one. Okay, so that means that this rectangle is 1. So if you add on that much more, then you're actually representing 2 now. Do you see that? Yeah. Did you see that? Okay. So if you want to turn something into 6 rather than adding on to it, you need to divide within. Yeah. Okay. All right, are you guys ready to talk about it? Or at least the first one? Adding with an area model. So, Armando, can you tell me what that, oh no, that's just the light on the whiteboard. There's like a box in the middle. That's just this, right? Okay. I was like, what's that thing on the screen? Okay. So when you look at the diagram for 1/2 and 1/3, and you say to yourself, I want to add these, what is the problem? The shaded parts are not equally sized. So if my goal is to combine things, then I must be combining things of the same size, which means I need to modify these pictures, right? Now, it's super duper 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 tempting to try to add on to these diagrams to achieve that, but I remind you, right? Anytime we're working with fractions, the second I drew this rectangle and one of them represent 1/2, that meant that this rectangle represents 1. So if I were to add, basically showing like 2 or 3 or whatever, right? I'd be showing something bigger than 1. So rather than adding on to, what I want to think about is separating. Okay? So I can cut these like, right? So in particular, I could maybe cut in half. Well, that's going to get tricky. So maybe instead of that, I could try cutting this into thirds. So if I cut this guy into thirds, now what does each of these new little pieces represent? Yeah, so this is 1/6 of 1 now. But, okay, so now I've got 1/6 of 1, but over here I still have the 1/3. So these are still not equally sized pieces, but what could I do over here? I could cut this guy in half. And now notice 6 equally sized pieces within my whole. So this is also 1/6 of 1. And so when I look at what I've got shaded, I've got 1, 2, 3, 4, 5, 6 shaded, right? Does that make sense? So quick comment about these diagrams. One of the things that I'm interested in is your ability to recognize that this little piece is 1/6 of 1, but it's also 1/3 of 1/2. Right? So I took my I took my half and I cut it into 3 equally sized pieces. So this is a way to show that 1/3. So when I say 1/3 of 1/2, what operation am I talking about? That's multiplication. Right? So we actually already just discovered how to show fractional multiplication. Do you see that? 1/3 of 1. So if I started with a half and I cut everything into thirds, then 1/3 is 1/6 of. Oh, cool! We just did fractional multiplication. That happened. Okay, so when you're doing the subtraction bit, does anything change? So if you're going to take away things, then you should take away things of the same size. Just as if you're going to combine, to be combining. So the only thing that changes here is that instead of combining the 3 shaded parts with the 2 shaded parts, I'm going to remove 2 shaded parts, right? So I'll start with a picture of 1/2. But then I'm going to say I need to remove 1/3. So how would you like to capture that? So you could say, all right, well, 1/3 is going to be something. This is not, let me draw this carefully because, yeah, okay, let me do this carefully. Or maybe I should exaggerate. Let me exaggerate the rectangle. I think that might make it easier. Okay, so this is my new 1. And I'm starting with 1/2. But I want to remove 1/3. So let me mark my thirds. Okay. So I want to remove this much. And my question is, how much is that left over, right? But the thing is, when I've marked a 1/2 and a 1/3, in order to make everything, like this chunk is not the same size as this chunk, right? So in order to make everything the same size chunks, I can actually do this, where now I've got my 6, right? And so I can see that I'm going to take away 2 of those 6, and what I'm left with is 1/6 of 1. So this is what I'm going to then take away, and what remains. A little bit trickier looking, I guess, with the subtraction, in the sense that when you're doing subtraction, you don't really usually draw. So this is actually something I saw a lot when we were doing like our base 10 models, was I would see people draw both numbers, and you don't really do that with subtraction. With subtraction, you draw the first number, and then you start like Xing out what you're removing, right? So you start with the first number, and then you like X out what you're removing. And it remains. Okay. Does that make sense? Okay. How do we feel about the area models for fractions, addition and subtraction? So far, so good? How does any of this change with a number line model? So now I want to do 1/2 plus 1/3 on a number line. Well, first off, what do I need in order to visualize 1/2 on the number line? I need a unit, right? So we can think of our unit as the distance between 0 and 1, right? So that was the quiz question, right? It's the distance between 0 and that number. So the size of that length is our unit. And, oh, shoot. Just realized something I forgot to do. That's okay. Poor Asina. She's going to be freaking out. Okay, it's okay. Sorry, it just really distracted me. Can we take a break for 2 minutes? Okay. Think about, or you don't have to take a break. You can think about how you're going to draw this on a number line. And I'm going to do something really fast for your classmate. We're good. I promised I would send her the quiz while you guys were taking the quiz, so she could still, like, not lose points in the class, right? Whoops. Okay. Okay. Have you drawn something? Still working on it? I'll get you started. We're still doing 1/2 plus 1/3. Do you have your number line model? Yeah? What you got? How do you do
Because
it?
I got the answer first, and then
So the whole idea is, again, trying to figure out how you would use the model to get to the answer. Okay?
Something like this, I guess. I tried to divide it into...
That's when you divide it into 6, and then
Yeah, but why?
why what?
Why do you divide it
Oh,
into 6?
because you have to find, you can't really add if you have 1/2 and a 3, like you can't split that separately, so
Okay.
first you find the common denominator, and then you split your unit from 0 to 1 into 6 parts, and then you just go 36 plus 2.
Okay. Is that how you would explain it?
In 1/2, the denominators aren't the same, so divide from there, since 1/2 of the 6 is 3/6, and then 1/36 is 6.
Okay. You guys like these explanations? You satisfied with them? All right, so if you were to look at a number line, the position of those numbers is where I've written them on the board, right? But in terms of being able to combine the numbers and actually figure out like where you land on the number line and what value you get, you should be thinking about taking this distance for 1/2, right? And then taking this distance for 1/3 and joining them to make a complete distance, right? But then the question becomes, when we do that, where did we land? So, what can I do with my number line to help me better understand where we land? Okay, so why 6? Because 3 and 2. So I'm getting the sense that this is one of those things that is either so uncomfortable for you already that you're like just not wanting to engage, or you're so comfortable with it that it seems too obvious for you to break down. It's one of those two things that I think might be happening, right? So I really, really, really want you guys to like reflect on the fact that everybody in this room knows that fractions is a hard concept for the majority of the human population. Yeah? It doesn't have to be. And it is your guys' chance as future teachers to change that. Do you get that? Like you guys are the people who influence how hundreds of future citizens of the world engage with numbers and whether or not they're comfortable with them and understand them and can use them when they need them. That's becoming your responsibility. It's a big responsibility. So I need you to care, okay? I need you to care. Otherwise I'm going to have a meltdown, okay? Of all of the classes that I teach, this is by far the most stressful for me because I am constantly thinking about that fact, right? When I think about you guys, I'm not thinking of you as students. I'm thinking of you as future teachers who will literally impact hundreds of children in your careers. So you ask yourself why I'm tough on you and why I push you. That's why. Because I'm thinking about the children, right? Okay? It's not just to be mean. I'm not trying to be mean. I'm trying to help you be the best teacher that you can be. Okay? And you have to teach math. Like, you can't run away from it. It's part of your job. And if you think you're going to get away with only teaching kindergartners and you never need to know fractions, newsflash, you're getting certified K-8. You go tell a school that you want to teach kindergarten and they already have enough kindergarten teachers, guess what? You can be teaching 5th grade. It's not up to you. You got to know this stuff. You have to be prepared. Okay? So please, please show me that you are as invested in the welfare of our future generations as I am. Okay? Because I'm a little nervous about, and I don't know if it's just because we're tired because we had to work last night and now we're back again this morning, but like hopefully by Tuesday you can show me that you're invested again. Okay? So when we're looking at this diagram, there is an exact mirror happening between the area model and the number line model. The only difference is instead of dividing the equal size, I'm going to divide lines into equal size pieces. Okay? So that's the only distinction between the two. Like, and so now I've got 1, 6, 2, 6, 3, 6, 4, 6, 5, 6. Okay? Cool? Okay. So now, one of the things that I really, 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 like, I meant it and I mean it when I label these things. Whenever you draw a model like this, you have to be thinking about this entire rectangle as your 1. That is critical. So I labeled 1/6 of 1 because I don't want somebody to look at this and think to themselves, oh, I've got 3 things, right? That's not what I'm going for. I'm going for like each one of these is 1/6 of the whole. Combined, that makes 1/2 or 3/6 of the whole. But that's not necessarily the way that we always talk about things. And so in particular, I'm going to show you right now a very, very common thing that you're going to encounter when you first introduce fractions, especially if you've been emphasizing a part out of whole, like that's not even the right way to say it. Part out of whole is a perfectly fine model. Where it falls apart is when people stop focusing on what the whole is and instead start saying things like 3 out of 4, 5 out of 7, 8 out of 10. Because notice when I start saying language like that, instead of saying 3/4, when I say 3 out of 4, it's really easy to just think like, oh, okay, well, I've got 4 things. As opposed to one collection of 4 things. Do you see the difference? So if you find yourself falling down that path on accident, then you'll end up with a situation like this, where you've got a student who thinks that 3/4 plus 2/4 is 5/8, very reasonably so, if this is the image that they have in their mind, right? I've got 3 out of 4 things, I've got 2 out of 4 things, so I have 5 out of 8 things, right? So this is something you will see. So how are you going to help this kid? What's the conversation going to sound like? So I want you to take a minute at your tables and try to practice that conversation with that child. Okay. All right, so you want to talk to me? What kinds of explanations do we have? How can we help this child? Yeah.
So we can say, like, instead of doing, like, each circle as a whole, try to explain that all 4 can be one whole.
Okay.
And the 3 shaded are the 3 parts of that whole.
So you could emphasize that this is one collection of 4 things, certainly.
And then explain, like, how 3/4 is the same, since you have 4 things inside it, when you're shaded, so it's 3/4 of that whole.
Mm-hmm.
Same with, like, the 2/4, the 4, the 2 shaded are the 4 things of that whole.
Okay. So 2 of the 4 things in that one collection are what I care about. And so then when I try to combine these, what's going on? You get more than a whole, right? So in particular, I could imagine maybe like taking this guy and saying, I'm going to shade him over here. And so now, instead of having a shaded circle, I have an open circle, right? And so now we can see that I have one whole collection and then 1/4 of a collection, right? And so you can see now that you have 1 and 1/4 or 5/4, right? Does that make sense? Feel good about it? Okay. by far like the most that you'll see. And then you can't even get mad at the kids because here's what's going to happen, right? You're going to get them over this hurdle, and then you're going to introduce fraction multiplication, and then they're going to go back to doing this again. Why are they going to go back to doing this again after you introduce fraction multiplication? Because how do you multiply fractions? You multiply the numerators and you multiply the denominators. Oh, so shouldn't when I add the numerators and I add the denominators? Like they'll revert and then you'll have to recorrect again. Right? So, okay. So this conversation takes a while. and it happens repeatedly. Okay, but just imagine how fast that correction will be if you've already laid the groundwork of having them want to make sense of the mathematics, right? So if you've laid the tone of this stuff is going to make sense in terms of when I see a fraction, I have a meaning for that. I'm imagining a 1, and I'm imagining equal-sized pieces within that 1. And then you've also laid the foundation for thinking about addition as this idea of combining things, whereas multiplication is having copies of things, right? Then you're going to see less of this struggle because the kids aren't going to be relying so much on these algorithms, right? The algorithms will just sort of be the convenient tool once they've actually mastered the idea. Okay? So let's talk about the idea. You guys already told me how you multiply fractions, but then there's this question of why. Why do we multiply the numerators and multiply the denominators and call it a day? Right? So rather than just posing you that question blankly, I'm going to give you a context that I want you to imagine to try to help us explain it. Okay? So Julie mowed 2/3 of the lawn, and her brother Carl raked 4/5 of what she mowed. So my question is, how much of the lawn has been raked so far? So what I want you to do is analyze the situation. Okay? What are the quantities involved, and how could you draw a diagram? So please, please, please do not perform any computation before drawing a diagram. Okay? Try to draw a diagram first and let that guide you. So can you walk me through how you created your diagram?
So it's 2/3 and 4/5.
Mm-hmm.
So I was thinking, what's a common denominator for both of them? So I got 15, which then would be 10/5, 10/15. So I shaded that, and then 4/5 would be 4/5 of 10. 4/5 of that 10th would be 8/10. So then I circled that area.
Okay. It also of it like, oh, interesting. But you started at January 15th as one.
Because 2/3 and then number one. Visualize that. Break it up evenly. And I got 15.
I definitely agree.
But it's a problem with the process.
It's just, it's hard to, I feel like it would be hard to motivate for a child to be like, well, I kind of knew it would be easier if there was 15 boxes, right? Like, well, how did you know that?
That, and I'm going to be honest here, before you said to not compute, I already went ahead.
Right.
Yeah.
So how do we actually start this conversation from scratch?
Well, first you want to see what 2/3 looks like.
Okay.
And then 4/5.
Do we need to know what 4/5 of just any old thing looks like?
No, you need to know what 4/5 of 2/3. Yeah.
What 4/5 of the 2/3 looks like. So if we focus our attention on what we've shaded for our 2/3, could you show me what 4/5 of that amount looks like?
You would have to break that up into 5 equal pieces.
Okay, can you do that?
That's what I don't get how to do it because it's already
So it's a little hard if you keep making vertical chunks, right?
square.
Hmm?
What did you do?
So because you've already divided in half that way,
Oh.
that makes it hard to do vertical divisions. But yeah, if you go horizontally, yeah. But where this is now your whole. Does that make sense? Okay.
So would you only cut the 2 pieces or the whole thing?
You cut the 2 pieces.
The 2 pieces.
Of the 2/3.
Okay.
Right.
So then,
Because that's your new whole right now.
so and you try to make it to 5, right?
I'd just like to point out that this is a area, so since it's a lawn, larger, I guess.
Like yours.
Can be useful. How we doing? Where's your lawn?
It's really
Whoa,
so this
messy.
is got 2/3
Mhm.
and then you mow 5 for so I would divide this into 5 parts.
Are those equally sized? Those aren't equally sized anymore. Yeah. So that's a problem.
So if I want to do it,
Can I do that? Because okay, this is okay. So there's 3 parts, 2 parts. Okay, well actually no. I don't know if that works. Okay, this is in fifths. 1, 2, 3.
Yeah, 1, 2, 3, 4, 5, and then he raked the, I guess, 4/5.
But it was 4/5 of what?
Of
2/3. So where are you seeing the 2/3?
Yeah, I don't know.
Okay. So is 1/5 plus 1/5 plus 1/5 plus 1/5 equal to 2/3?
No. That's
Put ours separately just because we didn't want that part to be like shaded
Okay.
in with it. So we put like the 2/3 of the one here, but then the 4/5 that actually had been raked.
So so each of these is how much of the whole?
Of this hole?
Yeah.
Or, oh, that's what we're...
You right? Because I'm asking how much of the lawn had been raked.
So we were just looking at like that.
What you guys got?
So we did, she explained it to me. Well, I don't know, I'm still kind of lost, but we did 2/3, or I cut this into threes, and then out of this is 4/5, so I did 5 parts, and we did the,
How did you divide? Are those equal sized parts?
well, isn't this like the whole, so then,
That does become the new whole. But what I'm asking is with your marks, it looks to me like this was originally 1/3, and then this was originally 1/3, and this was originally 1/3, right? Because you've got the black lines. But you divided this 1/3 into half, and you divided this 1/3 into thirds. So those aren't equally sized pieces anymore. Do you see that? Shall we? Okay, so I'm seeing a lot of difficulties with how you're you're trying to force it, which is common. So let's talk about some of the issues that I saw first, and then how we can address them. Okay, so some of the things that I saw was a lot of people saying, okay, here's 2/3, and then I'm going to divide this into fifths. Okay, but careful now, because maybe let me color code what I just did. So I had my 2/3. So this was my 2/3, and then I cut it into fifths. But if you look at what I've done, I've cut this third into half, but I've cut this third into thirds. So this piece and like this piece are not equally sized. So I have no way to talk about them. Okay? So that's a no-no. So instead, what we could do is say, all right, I've got a lawn, right? This is my lawn. And 2/3 of that lawn, so 2/3 of the lawn has been mowed. Now, 4/5 of that has been raked, okay? So that means that I should now be thinking about this as my new whole, right? So just that, this much now is my new whole, and I want to be able to show 4/5 of that. But you guys all notice that there's a problem, right? If I try to draw vertical fifths, I run into the issue that this line is not going to be in, it's going to sort of interfere with the picture, right? So instead of drawing my divisions vertically, why don't I go horizontally, right? So, okay, so let's draw. There's 1/5, there's 2/5, there's 3/5, there's 4/5, right? Okay. So then, if I think about this chunk, like this whole slice, this whole slice, this whole slice, this whole slice, right? These slices are 1/5 of my new whole. So then I need 4/5 have been raked. But now my question is, how much of the entire lawn was raked? Which means I need to be able to go back to the whole lawn and figure out how much the red checked parts are compared to the whole. Well, in order to do that, I need my whole to be divided up into equally sized pieces. So I could extend my division, right, into equally sized pieces. And now my question to you is, how many equally sized pieces are there in my whole? There are 15 equally sized pieces. And how many were raked? 8. Say, what? Right? Really cool, right? So this was 4/5 of mowed lawn. Checked. Right? But then when you zoom back out, you see 8/15 of the lawn. Notice that I'm writing 8/15 of something. Every time I write a fraction on the board, it's 4/5 of the mowed lawn, 2/3 of the lawn, 8/15 of the lawn, right? So I'm always reminding you what I'm looking at as my whole. I just realized I messed up my slide. Let me fix it. I really wanted So I don't know if you had looked this far ahead, but I had a reflection question down here, right? Which was, if we take away the context and just think about 4/5 times 2/3, how could we show this computation on a number line? I actually had written 2/3 here and 4/5 here. Why did I switch it? Why did I switch the order? To be a follow-up to this question. Not necessarily. And actually, I would argue that you don't start with the bigger chunk with this new order anyways. So when you read 4/5 times 2/3, one way that you could think of this is as 4/5 of 2/3, right? Which is exactly the context that we had here, right? I was interested in what 4/3 of 2/3 of the lawn was. Or sorry, 4/5 of 2/3. Do you see that? So if you had to mathematize this problem, right, so the computation that goes here is saying I'm looking for 4/5 of 2/3, technically, right, of one lawn. That's happening, right? So maybe we thought it looks weird to put those parentheses there. Okay? But this is the computation. But this diagram is actually how we could see really nicely how you get the result of that computation. Okay, but going back to a meaning of multiplication as this thing that can tell you, remember we talked about there was one meaning of multiplication that we didn't spend a lot of time on because we were really focusing and restricting ourselves to whole numbers. But I did mention, right, that if you have a fraction times a number, there was a special meaning of multiplication that was like the operational view of multiplication, where it's telling you like what part of that thing you're looking at. That was one of the meanings of multiplication that we have developed. So when I read 4/5 times 2/3, I'm reading 4/5 of 2/3 of something. Okay? So for the sake of time, I'm going to skip the number line question because this is directly relevant to what I just said. So when we multiply one fraction times another fraction, we get a fraction back, right? And so that means each of these is referring to some whole because each of those is a fraction. And so my question is, when we do this multiplication, two of these fractions are actually referring to the same whole. My question is, which two? Does that make sense? If it helps you, you might come back to this problem. This is saying 4/5 of 2/3 equals 8/15. So which of these fractions was referring to the same whole? What was the whole in this problem? Well, so it depended on the stage of the problem we were conceptualizing, right? So how did I start this process? We started with the 2/3 of the whole lawn, right? So this 2/3 is referring to the lawn, right? This 4/5 is referring to what as the whole? The 2/3, right? The mode lawn. So this 4/5 is referring to the mode lawn, which was only 2/3 of the whole lawn, right? Okay, but this 8/15 is 8/15 of what? Of the whole lawn. Okay, so which of those fractions are referring to the same unit? The 2/3 and the 8/15. Okay, so that generalizes. When you say A-beats of CD, this CD is of 1, whatever that 1 is. That gives you some fractional part of 1. But the unit on the A-beats is of this amount. Okay? So the unit for this guy is whatever this thing gives you out of 1. But this is out of the 1 and this is out of the 1. Okay. Okay. That says 2/5. So this problem is asking you to show what 2/5 times 3/4 looks like using a rectangular region. So you want to walk me through that process as a class? So I need a rectangle. And what's step 1? So divide that into fourths, right? Because when I read this multiplication, I'm thinking of this as 2/5 of 3/4. So I need to see 3/4 first. So this is my whole. I'm going to divide it into equally sized pieces. And 3 of those pieces are what I care about. Oh, but then I need, 2/5 of that, right? So now I'm just going to focus on this. And I'm going to pretend it's a new whole. And so if I wanted to show 2/5 of this, then I could divide this into 5 equally sized pieces. And so each horse is a piece, right? So here's one piece. Here's pieces. But now, whatever answer I get should tell me what fraction of the whole I'm looking at. So that means I need to have my whole divided into equally sized pieces. How many equally sized pieces are there? There's 20. And how many have I highlighted? 6. Cool? That, my friends, is fraction multiplication. Okay? Now, we don't have time to do division, but I want to remind you that this slide is actually not a new slide. This is something that we did when we first introduced the operational view of multiplication. And I just want you to remind yourself of how this works before coming back on Tuesday. But then on Tuesday, we're going to use what we know about division to make sense of dividing fractions. Okay? Have a wonderful weekend. And yeah. All right.